Hi, welcome to Real Learning Center. We are now focusing on real learning here. Moving on to Heat 4, which is the fourth video in this series. We have actually 6 videos in the series. The first 2 videos are on fundamental concepts like temperature and then heat, internal energy, specific heat, and thermal expansion. These are there in the first 2 videos. Please watch if you have not watched Heat 1 and Heat 2. And Heat 3, we talked about the heat transfer, how conduction and convection happens. So in the Heat 4, we are actually going to now talk about the radiation in a slightly more detail. So we just started the radiation in the Heat 3. Now we are going to continue and talk about radiation to a slightly more detail. Okay, so let's move forward. So now what we did learn in the previous video, conduction happens through solids, okay, and convection happens through liquids and gases, which basically carry the heat and move up and they get lighter. And for radiation, no medium required. You still get warm when you sit by the side of the fire. Okay, those are the 3 modes of transfer we discussed. And we also saw that there were some peculiar pictures taken. Okay. These pictures were taken using some special camera. Okay. And we said that these are all real pictures. And people and the things actually radiate light, okay, or what we call electromagnetic waves. So even the ice is radiating. You see the boy is holding ice in his hand. And earth is radiating. So all of this actually radiate when they are above 0 Kelvin. If they are just above 0 Kelvin, absolute temperature, okay, that means almost all the time, all the things actually radiate. So why do they radiate? So the question basically we asked was, even though dogs radiate, why do they radiate? So let's understand now this concept of why. So we start with some basics. Okay, so I'm just taking you through a lot of basics from electricity to magnetism in one slide. So just focus here. Okay. Now let's take one charge. What I'm showing there here is a red dot. Is actually a positive charge. Some charge. You must have heard about the charges. Okay, when you comb your hair and with the dry hair and try to attract some small pieces of the paper, it gets attracted. It's all because of the charged comb. It's called charge. Okay. So it's charged. So now whenever something is charged, if you bring another charge nearby that, so it will either repel or attract. Okay. So if you have a positive charge and get another positive charge near, it will repel. If you get a negative charge, it will attract. Okay. So there is a certain force on another charge brings nearby. Okay. And that force, how that force is, now at various distances. At longer distances, force is less. At nearer distance, force is more. To show how the force is, in which direction it will push or pull, okay, we draw something called as force field. Okay, so we say that there is a field which is around a charge. So this is an electric charge, and the field, this is actually an electric charge, and the field around the electric charge is called as electric field. Okay, there is electric field. Now what happens is so now I will make one statement. The statement is, a stationary charge gives out electric field, a constant electric field. Okay. Now what happens is, I will start moving this charge. Okay, I take the charge and move. So when the charge moves, you see the electric field around it is changing. Okay. So when the electric field around it is changing, what happens? So we've kind of done some experiments and seen in the classrooms that if I actually take one wire, okay, and conduct some electricity, put one wire around the iron and put some electricity, it will become a magnet. That means there is some connection from electricity to magnetism. Okay. And if you actually take one wire, okay, like this, okay, and put some charges moving inside that is called current. So the direction of current is from left to right here. You can see his thumb is showing the direction of the current. That means The other fingers are showing the direction of the magnetic field that gets created. That is a magnet that's get created around it. So what we saw was that if the charge was stationary without moving, okay, it created only electric field. Now the charge is moving, it created magnetic field also. Okay. So what are we concluding? We are concluding that if you have a moving electric charge, it will create the magnetic field. Okay. So we said that moving electric charges creates some constant magnetic field. So magnetic field is created around it. Now what happens is that this is moving at some constant velocity. So it is creating constant magnetic field. Now if the velocity is varying, if it is not going at constant velocity, then the magnetic field it creates also will start varying. Okay. So if you vary the velocity, how do you vary the velocity? Either you speed up or slow down or change the direction. That also varying velocity. Okay. So I take the charge and move up and down like this. When you take the charge, move and up and down like this, what happens now? The magnetic field anyway it creates because of the movement. Now change the magnetic field also keeps changing. Okay. So the changing magnetic field has this habit of creating electric field. Now you see the beauty. Okay, the beauty is whenever you keep moving the charge, okay, the magnetic field gets created, and that is also changing because you are changing the electric field. Then you are accelerating the electric field in fact. So that magnetic field also, since it is changing, it actually creates electric field. We have seen that earlier. Okay, when you look at basically a dynamo. Okay, a dynamo is what? It generates electricity. Okay, by changing the magnetic field around the conductor. If you rotate something in a dynamo, it creates electricity. What are we doing? We are changing the magnetic field. So whenever the magnetic field changes, you know very well that electricity will get generated, electric field will generate. So two things are happening. Now electric field is creating magnetic field and magnetic field is creating electric field. And when that happens, okay, we call it as electromagnetic wave. So continuously to the neighboring area, it keeps moving. Electric field converting into magnetic field into electric field. Keeps moving very, very fast. And that one is what we call an electromagnetic wave. So what have we understood? We have understood from this huge explanation, okay, which is you are going to learn in the future course of time in more detail with mathematics and all that. But remember, when there is this kind of a dance of energy between electric field and magnetic field, we call it as electromagnetic wave. Okay, and that electromagnetic wave, why was it created? Because a charge is jiggling up and down. Okay, so jiggling charge up and down creates electromagnetic wave. But where is the charge jiggling? In our body. So you can clearly see, I told you already that in every object, the atoms and molecules are always jiggling. And atoms and molecules have a lot of charge inside. Okay, protons is charged, electron is charged, molecules sometimes are charged. So ions are charged. So the whole of the an object inside, you can see that there is a lot of jiggling around. And every such jiggle around actually sends out a radiation. Okay, so what we call electromagnetic wave. So electromagnetic wave comes out of every charge jiggle. Okay, and that is what this picture is showing you. Now, what is the kind of electromagnetic wave that comes out? Okay, so this kind of a jiggling, how fast it jiggles, will ultimately determine what is the kind of wave it sends out. So what is the kind of wave? It jiggles very fast, it sends out a wave which frequency is very high. It jiggles slowly, it sends out a wave whose frequency is low. Okay. Now what has that to do with why should we worry about the frequency of it? So now if you watch it, actually, what I am doing is I am taking one nail. Okay, this is actually a nail. Okay, on the nail I am putting some blowtorch, very hot torch, which gives out the gas fire, and I heat up the nail. So when I heat up the nail, on the top of the nail you can see very clearly there is a different color. If you go down to in the nail, you can see color is changing. Okay. What are we observing? So there is some relationship with respect to color and temperature. So if you actually go down very much, then the temperature is not very hot, so you can't even see any color. Okay. But on the top you can see that there is a very bright color. So if you actually see, people have discovered or figured out that at 100 Kelvin you get red color. Okay. So which is somewhere at the bottom you can see red color. As you go up, the temperature is increasing. So after that you see reddish orange, then you see yellowish orange, then you see yellow, then you get yellowish white. Like that it keeps changing. So as the temperature increases, colors keep changing like that. You can actually match temperature to color. Okay. If you look at the color of something, you can say what is its temperature. Of a light source. Okay, I'm not talking about paint that you have drawn. Okay, of a light source. So if you look at a star which is blue, so you know what is its temperature. If you look at a star which is like reddish white, you know what is its temperature. One can find out by just looking at the color. Okay. So there is a very good correlation, relationship between color and temperature. Now, we basically whatever we call as heat, whenever we saw those pictures, what color they are. Okay, what are they, that kind of a boy giving out radiation, what color is that? Okay, to know that we have to understand what we call as electromagnetic spectrum. So what are the different kinds of wavelengths? Now it's a wave. Wavelength is actually have a length of the wavelength we call. Okay, so the wavelength of light or electromagnetic spectrum is what we are seeing here. If you come to the left side, you can see that this is actually longer wavelengths. Okay. On the right side, you have shorter wavelengths. Now, I am just plotting here. It is not a single wave. So I am just plotting, showing you that I can draw a spectrum like this, in which I can say the left one is the longer wavelengths are called as basically radio waves, and very high wavelengths are called as gamma ray. Okay. So in between this, actually there is something part called as visible light. Okay. Though light can come in various kinds of wavelengths, only that portion called as visible light is what our eyes can see. We call it as visible spectrum. Okay, and we call it as Vibgaya. Only that area you can see is actually visible spectrum. So it is going from here red to violet. Okay, red is the least wavelength, violet is the red is the maximum wavelength, and violet is the minimum wavelength of the visible range. You can go further than violet, okay, but we can't see it. We can go before the red, whatever you see, that also we can't see. That is infrared, what we call. Okay. So this is only visible area. Our eyes can only see a small amount of spectrum of light. There is so much of light everywhere. Out of some kind of light only we will see. The remaining light we cannot see. Okay, though it is there, but we can experience it through various other detectors. Okay. So actually, the phone messages, what you get, is coming through wireless radio signals. They are also electromagnetic. So phones can see them and receive them. You cannot. Okay. So phones have that ability. Now you see, we can also represent them in terms of frequencies. Now higher wavelengths means lower frequencies, lower wavelengths means higher frequencies. So we have written, there is a formula relating those. Okay. Now you can see that frequency matched to the colors. Very clearly you can see different colors shown there. Now the area that we are interested in as heat, we call heat, okay, is this area which we call infrared region. Okay. That means before red, infrared, less than red, frequency less than red, wavelength more than red. Okay. In that area, you cannot actually see it with our naked eye. Okay. If you use a night vision goggle, or if you use a night vision camera, you can see the infrared. Okay, the technology that makes it possible. So the infrared area is where our bodies radiate. Our bodies are anything that they radiate in infrared region. So we can't see, infrared cameras can see. But the beauty of that infrared radiation is it is actually, if you bring it near our body, it vibrates our body molecules very fast and hence can give us heat. So infrared radiation is something we call as heat radiation. Other radiations don't give that much of heat because that vibration cannot vibrate our molecules. So for us the heat is all about what burns us. That's what we call heat. So what burns us depends on what molecules we have on our skin. Okay, our kind of molecules actually vibrate only when you send infrared, and hence we call it heat. Okay, that is the area basically we call heat. Okay, so now what actually happens is that if you take any material, okay, if you give out radiation to that material, okay, multiple things happen. Radiation means, you remember, see here, actually I'm writing this wave because light in the waveform is what we call radiation. Okay, radiation comes there. It's actually a sprite, it comes there, but we show it as a wave. Okay. So that radiation actually either reflects, okay, it's called reflection, we call it as it reflects, or it gets absorbed inside. Okay, or it can also transmit to the other side. Okay, so things that can happen are radiation which is reflected, or absorbed, or transmitted. All the three things can happen. Okay, now if you have taken, let us say, certain frequency, let us say red. Okay, if you send red, okay, through that, what comes out is also red as a reflex, and what gets transmitted also is red. Okay, but the absorbed material actually, so whatever you have sent here, all of that did not go away or get reflected. Some of them got absorbed inside. Okay, the things that got absorbed inside, they can't stay there inside. Like they have to actually go out. Okay, they go out as its own radiation. Okay, the radiation of the object itself. So they go out as its own radiation, and its own radiation when it goes out, and that depends on how much it is vibrating. Okay, and it depends on the material. Its own radiation depends on the type of material, and hence its frequency is not same as the frequency that was actually given to it. Okay, so whatever it has, it will give out its own frequencies. That means if you, even though you have given red here, what gave out is not red, it is something else. It may be infrared. Okay, it gives out its own material, its own radiation. Okay. So please remember that whatever radiation you give it to a material, some part gets reflected, some part gets transmitted, some part gets absorbed, and absorbed radiation gives out after some time as its own radiation, and it will be at a different frequency. Okay. Now, what is important is that we say there are something called as black bodies. Okay, black bodies actually mean the ones which are black. They all absorb most radiation. Whatever radiation you give to the black bodies, they absorb. Okay, so why do they absorb all the radiation? Why do they absorb? So the answer to that is, why do black bodies absorb all the radiation? That is the question. So see the tricky answer. So we call them black because they absorb all the radiation. They don't reflect or transmit any radiation. They absorb everything. That's why they look black. Okay, it is the other way around, in the sense that since they absorb all the radiations, we call them black. It's not like black bodies absorb all the radiations. Okay. Since they absorb all the radiations, we call them black. So now once they absorb all the radiation, so let's just look at this part. Okay. Now, can you tell me what colors a red plastic chair absorbs? One red plastic chair is there. What color does it absorb? I think you can answer this. Okay. So actually, all the colors except red it absorbs. Only red it reflects. So, and it comes to your eye. Oh, you see a red chair. How can you say it is a red chair? Because it has absorbed all the other colors and given you red. That is why it is a red chair. A blue chair absorbs all the colors except blue. Blue it reflects. Oh, yeah, it is blue. We can say. Okay. So the black body, like white looks black because it doesn't give you any color. It absorbs everything. and not only it absorbs everything, once it absorbs, it can't keep it with itself. Okay, so after some time it will actually send out or radiate all of that. They become very hot. That is why black bodies, we keep it outside, any black thing, it becomes very hot because it absorbs all the things. And when you bring it inside, it is like if you go near it, it's very hot. Okay, it is actually radiate. It radiates in many frequencies, various frequencies, black bodies. Okay. So that is why black body radiation is studied, because it's a big absorber and big also radiator, black body. Okay. So likewise, if you see, okay, sun actually sends out light and earth absorbs, and afterwards earth transmits. Okay. And when earth transmits, actually atmosphere absorbs, and atmosphere sends some out, some actually it gives in, and it gets heated up. Okay. So you understood, earth actually, sun sends certain radiations, a part of it earth absorbs, part of it reflects, and then what happens? After some time, the absorbed radiation, it gives out at various different frequencies, and those frequencies cannot escape, they again get absorbed by the atmosphere. Okay, atmosphere actually becomes slightly warmer because of that. Okay, this makes actually earth a livable place. Do you know what would have happened if this would not have been there? If let's say atmosphere is not there, and if let's say earth is not giving out its own radiation, then just by earth's radiation, if you wanted to live at the distance at which our planet is there from the earth, if you calculate what is the kind of temperature you can get, okay, you would have been at minus 18 degrees centigrade. Earth would have been at minus 18 degrees centigrade, and you and I wouldn't have been there. Okay, the fact that warming is happening is because is the reason why we are there on the earth. That is, warming is helping us. But please understand that this warming is taken to the next level, okay, where we call global warming. Too much of warming, what will happen? That we will see. Okay, before that, we'll see how much percentage goes where. Okay, just a small understanding of how much percentage goes where. If the sun's rays are coming to earth, a great percentage of that actually is absorbed by the earth itself. Okay, about 10% is actually 19% absorbed by the atmosphere. Okay, 19% absorbed by the atmosphere, and then earth actually absorbs 51%. Half of the sun's radiation is absorbed by earth, the surface. Okay, and out of that, only some 4% is reflected back directly. 4%. Okay, and then about clouds actually reflect around 20% of it. The clouds reflect around 20%, and you can see that some 6% is reflected by atmosphere. Okay, this is basically how the sun's energy gets distributed. So that will tell us that a lot of energy is actually absorbed by the earth. Okay, now whatever is absorbed by the earth will actually finally comes out. It is not the reflection. The reflection is just reflection. Okay, that means same frequencies. Absorbed ones actually will be given out later. Okay, so that as its own radiation. In the night, actually, if you go and watch Earth, okay, from space, this is how you can see. This is actually taken from an infrared camera, okay, from a satellite on the night side of the Earth. Okay, there is no sun is on the back side. Okay, so it looks so beautiful. Okay, that is because actually all those areas on the Earth are actually, depending on the temperatures, are radiating certain kinds of radiations. Okay. So this is how it looks like when you take it from the night, in the night. And if you actually look at so-called overheating of the Earth's surface, let's understand what is meant by overheating in the Earth's atmosphere. So you have your our Earth here, not our Earth here, and on the Earth, let's say this is our atmosphere. I'm just showing some atmosphere part. Okay, and you get basically sun rays into the Earth. So now once sun rays falls onto the Earth, a lot of the rays actually get reflected. Okay, and 51% gets actually absorbed inside. Okay, and when they are absorbed inside, they are also reflected back. Okay, now the reflected ones actually, these are the ones which are reflected. they escape the atmosphere and go back. You know, the light which came inside, it is a similar light, it can go out. Okay, because what actually can leave the atmosphere or what can stay in the atmosphere it depends on the frequency of the light. Okay, certain frequencies can escape, certain frequencies get absorbed. Okay, now incoming frequency and our returning frequency both are same. Okay, so then it will go away. Okay, whereas the absorbed ones that will be released a little later, what will happen to them? They are actually sent at different frequencies, mostly at the infrared level. Okay, and these frequencies actually cannot escape the atmosphere. So when they cannot escape the atmosphere, they actually get absorbed by the atmosphere, and the atmosphere gets hotter, warmer. Okay, and this part, what we call is as global warming. Okay, so it depends on what you have in the atmosphere. If you have more of carbon dioxide and more of these gases which are actually can absorb more heat, so then what happens is this atmosphere gets heated up more. So that is why we call it as global warming. It's also called as greenhouse effect. Okay, so to reduce the greenhouse effect, what to do? People are basically figuring out and see whether we can reduce the carbon dioxide in the atmosphere. How can you utilize certain plants to convert carbon dioxide into oxygen? Many such things people are trying. Okay, because we want global warming to happen, and we liked the warming till it went from -18 to the today's 20 degrees or 25 degrees. But we don't want it to go much further. If it goes much further means it's very harmful to us. So we want to arrest it, reduce it. So that is why global warming has become a big threat for us for future. Okay. So now we have completed the understanding of radiation. So we kind of finished almost all the topics we talked about, from temperature, heat, internal energy, specific heat, thermal expansion, Newton's law of heat, cooling, heat transfer, all the radiation, everything we found out. Now the next video will be on state change, how liquid to solid, liquid to gas, gas to liquid, all this can happen, and the beauty of that part of the physics we will try to understand in the next video. So like every time before, I'm again going to ask one or two simple questions for you to think about. It's called thinking questions. Okay, since energy is radiated by all objects, why can't we see them in the dark? So you said even the ice will generate energy, radiate energy. Why can't we see it? So I have answered this question already. I think think about it. Okay, the second one is, if you keep, this is an interesting question. Okay, if you keep a red chair in a room filled with blue light, okay, let's say you go to a room full of blue light and no other light, put a red chair there. Now, what color do you see? How does it look like? Chair. Okay, so that is, you can even try it out. Okay, it will give you an idea. So global warming is actually highest on Venus. Okay. On Venus, planet Venus, global warming is highest. Its average temperature is 450 degrees centigrade. Okay. We are like 25 degrees centigrade. That's what we are looking at. There it is, 450 degrees centigrade. And can you find out why? Why is it such a high global warming in Venus? So figure out the answer to these questions and enjoy heat. Thank you. Bye.